Well, first of all, I'm quite happy to be back at IMPA. The first time I was in IMPA, I think, was 38 or 39 years ago. At that time, of course, IMPA was in Luis de Camões, and I still remember the building, the historical building. Then I was back at IMPA when this building was inaugurated, so I really feel like a friend of IMPA. So, the topic of today, I've seen I've been listed under algebra, and I don't want to disappoint you because there will be algebra in this talk. Although the topic is really a topic in analysis, I mean true analysis, not formal analysis. So this is the topic. This joint work with my daughter. In fact, she was responsible for dragging me into this field because she posed me at some point a problem which was basically a geometric problem. And at the beginning, I started to work on this problem without knowing anything about the application to the Schrodinger equation. It took me some time to understand that the geometric problem has something to do with true problems in analysis. I think I now understand it more than before. Now, why did I do that? So I like to say it this way, that there is this Peter's principle, which is one of the Murphy's laws, that says that you rise up in society until you reach your level of incompetence. Of course, it's almost a theorem, because if you are competent, then you can continue to go up. And so I will try to see whether I've reached my level of mathematical incompetence. So the normal form, of course, is not really a completely technical name. It's a method. And the method is, of course, that you start from some equation, in particular, this would be a nonlinear PDE, and you try through this method of normal forms to study some solutions, special solutions for the equation. So here, if you look at the equation, so this is just a Schrodinger operator, and then this is the nonlinear term. U is a function which is defined on a torus. Now, why the torus? The torus, of course, because it simplifies our treatment, not because there is any magical reason. Of course, if you could do it also on Rn, and then there are phenomena which are different, the techniques are much more complex, so we do it on the torus. Now, why the nonlinear Schrodinger equation? Of course, there are many nonlinear equations which arise in mathematical physics, and the nonlinear Schrodinger equation in a way is simpler than others, so although it's quite complicated, it's a good start if you want to do other more complex things. So here, this is the Laplace operator in these variables, and this can be defined for all powers q, and you can also add some other terms which I don't want to do, and there is this constant. Anyway, there is some technology, and I want to simplify the technology to maximum because it's already fairly complicated. So I will set this constant equal to 1, and I will only discuss today the q equal 1, which is the cubic, which is also the most famous of this class of nonlinear equations. But some of the things I would say, in fact, most of the things I would say actually apply also to the other cases. Now, how do we want to treat this equation, and what kind of problems we're asking about this equation? So, first of all, we write it in Fourier coefficients. So you can think that the evolution of the function is just the evolution of the Fourier coefficients. So each Fourier coefficient evolves in some way, which is, of course, described by the nonlinear equation. And if you forget about the cubic term, if you just take the homogeneous Schrodinger equation, then the solutions are quite simple, and they are a superposition of waves, of this kind of waves. And if you look at dispersion rule, then you see that these waves have different speed. And so you want to see what happens to these waves when you excite the nonlinear interaction. And what do you expect, or not what you expect, what can you hope? So, if you start from a solution which depends only on finitely many frequencies, if you look at the formula before, then you see immediately that this is a periodic motion. And what you hope is that if you perturb the equation, you hope that this periodic motion is somewhat preserved, that you cannot, well, of course you can also ask whether there is still a periodic motion, but the most logical thing is that these periods are slightly perturbed, and so you will get only something which is quasi-periodic. I don't want to give you the definition, but quasi-periodic is essentially something which moves ergodically inside a torus. So this is essentially our goal. This is a problem which is justified by the fact that we can actually formulate this nonlinear equation in the Hamiltonian formalism. So I assume you have some idea what is Hamiltonian formalism. So there is some kind of Hamiltonian function. In fact, it's a functional because it's on the space of functions. And then if you can set up this this formalism, which I will explain in a moment, then there is this Hamilton's equation that express the dynamics. And in fact, you have these conservation laws, which are typical facts about Hamiltonian formalism, momentum and mass, which are defined in this way. And let me be more algebraic. And so what we write the functional as a function of the coefficients, or the Fourier coefficients. So the Fourier coefficients are these parameters. Of course, there are infinitely many parameters. And the symplectic form is a very simple symplectic form, so except it's in complex coordinates. So it's a usual symplectic form of mechanics. And the Hamiltonian is this polynomial, if you want, of degree 4. Of course, it's a polynomial in infinitely many variables, which of course poses some analytic issues, which I really don't want to discuss, but let me just say that the formalism is this formalism for infinite analytic power series. The rules are the rules of Poisson rules or Poisson brackets, the usual rules which are given by these things. And then, of course, if you want to make sense analytically, you have to restrict your UK so that these are coefficients of some functions which lie in some suitable Sobolev space. This I think I will skip because otherwise I will not go very far. But I can assure you that there are some true analytic spaces on which this algebraic formalism actually takes place. So let's use a little bit of algebraic formalism. The action by Poisson bracket of a function f as an operator, you think you write it add f is like a joint action. So the dynamical system, as I already mentioned, generated by Hamiltonian is given by this by the evolution of this equation, and so when you integrate these equations formally, at least, this is just the one parameter group generated by this operator. So there's the exponential of this operator. Because this at this point this is purely formal, and you don't. It's tautological if you want. But so it's just a way of setting up the formalism. And then usually, of course, what do you do in mechanics? In mechanics or in these Hamiltonian systems, one thing that you try to use are some kind of conservation laws, and so you try to look at functions which Poisson commute with the Hamiltonian, and you call them integral motions. And if you have enough integral motions, if you have a lot of integral motions, you have a completely integrable system. These are the easiest systems to study. And once you have a completely integrable system, of course, it's easy to describe or to integrate the system, usually. Well, it's easier. It's not completely easy, but, and typically an example could be this. If you have a Hamiltonian which depends only on this square, moduli square of the coordinates, then basically the Hamilton's equations have this very simple solution. So you have an explicit integration of the form. Now, when you look at nonlinear Schrodinger equation, it turns out that, in fact, in dimension 1, it is completely integrable. And this is a classical theory of Sakharov, I think. But as soon as you go in dimension greater than 1, which is our topic essentially, then complete integrability is lost. And then what can you do when you lose complete integrability? Then there are several methods, and well, this maybe I skipped this thing. And the method is based on the following idea, which I think goes back to Poincaré and Birkhoff. If your Hamiltonian has this quadratic part, which if it were just this quadratic part, it would be just some independent oscillators. And then there is this other part of higher degree. And then you know that if you take a monomial in your symplectic variable, this is an eigenvector of this quadratic part. And the eigenvalue is given using this rule of commutation. So if you have a linear combination of these things, then you have the corresponding linear combination. And the idea of Poincaré and Birkhoff is that you can make coordinate changes, symplectic coordinate changes, which actually cancel the monomials which do not commute with this term. So if you have a term which does not commute with the quadratic part, then you can cancel it. And the idea is that if you could carry out this procedure to extremes, maybe you could cancel almost everything, leave only things which commute, and maybe if you are lucky, these things commute with themselves, and then the system becomes completely integrable. Of course, this doesn't work. It cannot work because the system is not completely integrable. And what happens, in fact? Well, what happens is that if you really do this algorithm completely, usually you get divergent procedure, and so you cannot do it forever, otherwise just formal. And this is really one of the subtle points of perturbation theory, that there are, in physics, you know, and there are a lot of perturbative methods which work. On the other hand, if you try to look at them completely as a complete algorithm, they give you divergence. So, still you can do this procedure, and we want to do it for the NLS. So in this case, the quadratic part is this, and you see these coefficients are integers, and the fact that they're integers, if you remember, maybe you don't remember, but anyway, suppose you remember the previous slide in which I gave you the eigenvalues, you will produce a lot of monomials which have eigenvalue 0, so a lot of monomials which commute, and which you cannot cancel. So if you start this algorithm of Birkhoff, then you see that this produces this thing. So let's pause a little bit on this formula. So here was the quadratic part. In the part of degree 4, what happened is that before I did not have this constraint which is underneath. I only had the constraint above. The constraint which is underneath just expresses the fact that we have saved only the terms which commute. Of course, the price that we pay is that once we keep only the terms which commute, the price that we pay is that there are infinitely many terms which have appeared now in all degrees higher than 6, in degree 6, 8, and so on. So now, at this point, the strategy that one follows is that one considers this part as sort of the main part of the Hamiltonian, and this other part should be some kind of a perturbation for the Hamiltonian. And so at this point of the game, you have to make all kinds of statements which make this idea work in some sense. So first of all, you have to show how you study this part, and then you have to show why it is really correct to consider this as a perturbation. Why can you sort of play a game which first studies this part and then from this study produces solutions for the entire equation. Okay, so we call this, so at this point I drop the part of degree 6 and higher, and we call this, for instance, a toy model. I mean, it's actually a very complicated toy. And, but the idea is that, first of all, we want to study the dynamic associated to this Hamiltonian. And then, after we have studied maybe some solutions of this model, then there are methods which pass from this model to the true equation. And I will tell you in a moment what are these methods. So, let me first of all say what are properties of this model. So now here you have this Hamiltonian in this infinitely many variables, and you try to restrict this variable to a subset. So after all, if you have a function in some variables, you can set some of the variables equal to 0 and try to see whether you can study the function in the remaining variables. Now the point is that when you do Hamiltonian mechanics, you cannot just set a certain set of variables equal to 0 and study the dynamical system on the subset where these variables are 0, because this makes sense only if the Hamiltonian vector field is tangent to the manifold that you have defined. So the first question is that you have to understand if there are actually subspaces which are stable under the dynamics. And in fact, what we will see in a moment is that there are infinitely many such subspaces, and even there are infinitely many such subspaces, such that when you restrict to this subspace, then the system is completely integrable. And let me explain how you do this. This actually is a little game which is very similar to what you heard yesterday, if you heard the talk on bootstrap percolation. And let me try to convince you why this is similar to the bootstrap percolation talk. So the condition that a space is stable so that the vector field is tangent is that if you take 3 points in the set that you have taken, and they form a vertex, 3 vertices of a rectangle, also a 4th vertex is in the rectangle. So basically, if I have you have some points, for instance, like this. So you start from these frequencies, and you see these 3 vertices form the size of a rectangle. So if you only take these 5 elements as your set of parameters, this will not give you a stable manifold. So you have to add this thing. But then once you have added this thing, then this also forms the side of a rectangle, so you have to add this thing. And of course, if you add more, then this would continue like this, and this is exactly the infection one of the possible infection model of percolation. Which just means, from a dynamical point of view, that if you start from a solution which contains some frequencies, then it will excite all the other frequencies which you have to add in order, which percolate according to the, or are infected according to the terminology of yesterday. So I tried to make some connection with yesterday's talk. I think it actually makes complete sense, and you can, but of course the phenomena are slightly different. So, but I say that, when we want this to be completely integrable, then we really don't want any rectangles like this. We only accept degenerate rectangles. Of course, you can sort of degenerate a rectangle like this. So how do you make sure that there are only degenerate rectangles? Well, it's quite easy. You just draw points so that they never form straight angles. You can, of course, draw a lot of such points which never form, maybe that, this may be straight, I don't know. Okay? So there have to be integral points, and clearly you can choose, if you choose points at random, you could say, maybe you could give some distribution, probability distribution, or you just say it intuitively. Usually you will not get that they form straight angles. So for most choices of such points, you will have that the restricted system, which was this one, is in fact completely integrable. So what you have done, you have started from your Hamiltonian, you have done this symplectic change of coordinates, which isolates this terms up to degree 4, and you concentrate on these terms of up to degree 4, and then you see that inside the dynamic of this system there are infinitely many subsystems which are actually completely integrable. So you can integrate them and you find a lot of solutions for this toy model. But now, what is the problem? The problem is that you want to pass from the toy model to the true equation, and then you have to use some kind of algorithm. And the typical algorithm that we want to apply in our case is the so-called KAM theory, which is from Kolmogorov, Arnold, and Moser, and which is actually a completely algebraic algorithm in a way, in which you start from your solution and then more or less stepwise try to make changes of coordinates so that it becomes a solution for a higher and higher order of perturbation. I certainly don't want to discuss the KM algorithm. So here you have to do a KM algorithm, but you have to do it in infinite dimension. And the main obstacle of the KM algorithm is not the algebraic, well, in fact it is also the algebraic algorithm itself. So there are two obstacles. One is that you need some non-degeneracy condition, which I will try to explain later, that make the algorithm at least formally work. And then there are analytic difficulties, which are called the problem of small denominators, that it's quite complicated analytic issue. Of this thing I will not speak. So, if the algorithm works, if you are in a good situation in which the algorithm works, then you can expect that for a small perturbation of this system, you have the persistence of sort of infinitely many stable tori, parameterized by complicated Cantor-like sets. This is the typical picture of the KM. Of course, if it is not completely integrable, you also have orbits which behave in different ways. So there will be very different behaviors according whether you are in this Cantor set or in the complement of the Cantor set, and the whole problem, the dynamic is in fact extremely complicated in general. So anything you can say usually is a useful information for the thing. And so what we want to do, we want to prepare our equation in order to be ready for the KM algorithm. So the normal form is essentially a preparation of the PDE so that it is ready to be fed to a KM algorithm, which will be, in any case, a rather complicated analytic problem. Well, especially because we're in infinite dimensions, so there are infinitely many small denominators and so infinitely many singularities. You have to control all these things. So this, but anyway, the fact that this can be done actually has been understood for some time. There are several works by several people. I didn't try to write a historical background of this because it's quite complex, but there are several names, maybe Peschel, Bourgain, Cooksin, Eliasson, and several people have contributed to this. And in any case, you have to start from suitable solution or the apply perturbation theory. And then if you have this normal form, which is non-degenerate in some sense, which I will try to explain, then you can do it. So let me try to say what we need to do in our case. So as I said, we start from a choice of this set of frequencies which give you the initial solutions. So we start from an initial solution which is the solution of the linear equation, which depends not on all frequencies but on some kind of generic frequencies. And the rules I told you, the first rule is this simple rule that I say that the angle should never be straight. So that's quite simple. Well, then you give some names, you call these things tangential sides, and you have the other frequencies you have not used are the normal sides. Now, if you have any familiarity with any kind of algorithm in algebra or in differential geometry and so on, if you have something which lives on some subvariety and you make some perturbation, usually the first thing you have to understand, if you want to understand anything, you have to understand when you look at the normal directions, if what you're doing is in some sense non-degenerate. This is what you do when you do Morse theory or when you do Hensel's lemma. Non-degeneracy is sort of tells you that you can, that the first obstruction to perturbation is solved. So that's usually a non-degeneracy condition. Once you have made the first step of perturbation, then you hope that for some miracles you can continue at all steps of perturbation. So we start from this. And as I say, we try to apply perturbation theory around these solutions. And then we make a change of variables and we introduce some parameters. This is sort of a trick, but so just take it as a fact of life. It is useful to do this trick. So we put this in action angle variables, and we think of this as parameters, and this we keep as the dynamical variables. So the dynamical variables in which we have Poisson bracket are these, and these are just parameters which parameterize the orbits. So if you want, this is a trick. Accept it as a trick. Well, once you do this, you substitute in the formula, and then you take some kind of a new leading term, and so the dominant term of this formula, and then the quadratic part essentially becomes this. So some variables have changed name because of because you have this yi, which is related to the absolute value of this thing, and these parameters now become coefficients. So you have the quadratic part is this, and then there is a complicated part. The complicated part is the one which describes the interaction at first order, which is the order 2, the interaction between your solution and the other part of the world, the normal part of the world. And this is the formula. Now, this formula is a bit complicated, so we have to sort of look at it. So this is a sum over certain choices of indices, and there is a star which I will explain in a moment. So the only thing I have to explain is what is this choice of indices. These are terms in ZH, K bar, these are terms without bar, and these are terms with all bars. And so the only thing I have to explain what is the sum over, where does it come from? Well, this, of course, it comes from the monomials that we had before. Before we had some monomials. Maybe I should go back. Sorry. We had these monomials here. Now we are making some substitution in these monomials, and then taking the leading term in each monomial. So in each monomial, if we substitute two variables, will come from the set. I'm sorry, this is not the thing. This is I'm looking at the entire thing. This is the restricted. Okay. Yes. So here is where I'm looking at, and I substitute two of the variables in the set S and two outside the set, and I look at what happens. So if I look at what happens, I get this rather complicated formula. So this formula contains these normal variables. Here there are now normal variables, and here the tangential variables here appear only through this angle. That's what happens. So the interaction between the tangential and the normal variable appears in this way through some kind of phase change. Let me explain what is the sum. So the sum just is a transformation of these rules or conservation laws that I had written down, that the sum is of the ki is equal to 0 with some signs, and the sum of the squares of the absolute value is equal to 0 with some sign. And this is transformed by this, and this is the rule. So this sum star means that you're looking only at four tuples which have these two constraints. So this is a linear constraint which comes from conservation of momentum, and this is the quadratic constraint which comes from commutation with the quadratic part. And the other sum is slightly different, and it's given by this other formula. So let me see, if you look at this thing and you don't see what it means, then the best thing is to look at this thing from a geometric point of view. And from a geometric point of view, you see that you can define hyperplanes and spheres associated to pairs of vectors. So one is hyperplanes which are orthogonal to the line through these vectors, and this is a sphere which has a diameter, these 2 points. And then our condition is simply visualized in this way. So the sum star is the sum over the rectangles of this type. And the other sum star is over rectangles of this type. So each one of these terms of the sum corresponds to the fact that you're taking either 2 points in the rectangle associated to Vij, or these other 2 points associated to another rectangle, which also is related to Vij. So there is a geometric interpretation of the terms of this quadratic Hamiltonian, which gives you the interaction between the tangential sides and the normal sides at first order. Now what happens, you see, these things are really interactions. So when you have such an edge, this means, or such an edge, this means that you have a term here, a corresponding term, So a corresponding term means that you have some kind of interaction. Now the problem is that when you have an interaction between two sides, then there could be, so between side A, the first side and the second side, then there could be another interaction between the second side and the third side, and then so on. There could be several interactions. So here we have just understood the two terms interaction, but then these things can propagate. And so what do we have to understand? We have to understand exactly the propagation of these interactions, which means that we could have 2 points like this, but then this point here could interact with another point according to another rule of the same type, but for some other vectors. So this vector here could interact with another one using another vector. Okay? So there are all these interactions which appear. And how do you understand these things? Well, okay, before I say how do I understand, you see, one of the main theorems that we have is that we can actually make a change of variables so that we eliminate all the interactions between the variable, the normal variables, and the tangential variables. So before the interaction was given by all these phases, and the idea is that you want to eliminate you want to synchronize, if you want, all these systems, so that it decouples with respect to the tangential side. So if you can decouple the system, then if the decoupled system, which is given now by this Hamiltonian, is sufficiently good, which of course is another issue, then you can hope that to continue in your KM algorithm. So there are two steps. First you want to decouple the system, and then you want to make sure that this system is actually fairly good. Fairly good means what? This is an infinite dimensional Hamiltonian system. You want to, again, decouple it into infinitely many independent finite dimensional systems, and you want these finite dimensional systems to be very good. So what kind of problems you get? Well, and very good actually means this, that you can actually essentially bring to diagonal form this system. Actually, it's not completely true because there are some hyperbolic directions, but there are some technicalities. Essentially, you can bring it into diagonal form. And once you have in diagonal form, then whether it's good or not depends whether the eigenvalues of this diagonal form are sufficiently separated or not, which is another issue. So, in fact, you have this other problem, this other property, that this is, in some non-degenerate, there is a technical statement which is called the Melnikov condition. And once you arrive at this point, then you develop the KM algorithm and find the quasi-periodic, the global quasi-periodic solutions of the nonlinear Schrodinger equation, of the original nonlinear Schrodinger equation. So, as I say, this is a highly non-trivial, but I will not discuss. So, how do you study this monster? So, you study it as an operator. It is a quadratic expression. And by rules of Poisson bracket, you see that you can study as a linear operator on this space. Oops, sorry. On this space, where did I go? I just went back. You study it as an operator on this space of functions. But this space of functions have a special constraint between these parameters and this parameter here, which is given by this identity, which actually means that these functions Poisson commute with momentum. So it's the conservation of momentum property. So you take the space of functions which preserve momentum, you act with this operator on this space of functions, and then you want to study this linear operator acting on the space of functions. So the part D acts diagonally, and then there is this very complicated part, which is what you have to study. So how do you study? What do you want to do? How do you study? So we want to show that if we make some further constraints on this site, then this is block diagonal. Block means that you have fine dimensional blocks and non-degenerate in a way which we are to explain. And we'll do this by introducing a combinatoric and a geometric graph which describes the interaction site. So it's something like what I had here before. So let me try to explain this idea. So let's start with a very, very simple idea. So this is, if you are lost by this at this point, or maybe this can wake you up because it's a very simple idea. If you have a matrix, finite or infinite matrix, and you want to decompose it into blocks, what do? You take a graph which has as vertices the basis vectors, and then whenever you have a matrix entry which is different from 0, you connect these two vertices by an edge. It's just a way of remembering when is that two things are connected by the operator. Then if you decompose the basis into the connected component of this graph, then of course you have decomposed in a very stupid way, but sufficient for us, you have decomposed the operator into blocks. Just collect into the same block the things which are connected components. And that's what we have to do with this operator. In this case, we call this graph, we call lambda S. So the operator is on this space, which has a basis indexed by the normal sites, but no, by certain things, which I will remind you. And then we have to study this graph. And the study of this graph is a mixture of combinatorics and geometry. And so let me explain the combinatorics. So the combinatorics is in two steps. First, you do the combinatorics, something which is well known in group theory, which is the Cayley graph. So what is a Cayley graph? Cayley graph is a very simple notion of group theory which is used to understand basically generators and relations in a group. So you take a group and you take a subset of this group, and then you want to construct a graph in which each edge is marked by an element of the subset. Then you take an action of the group on a set, and then you define the graph which has as elements the vertices of this set, and if you have two elements of the set, you join them by an edge. If you can go from one element to another using one of these elements X. Okay? So this is what people do in group theory. You take a set of elements perhaps which generate the group, and then you have an action and you join two elements by an edge, and you mark it by X if one is obtained from the other going with X. So in our case, what we take as group, we take the semi-direct product of the standard abelian group with Z mod 2, which represents the conjugation essentially. And then we take a set, these elements here, which are exactly the elements which appear in the frequencies or in the quadratic Hamiltonian that we want to study. And then we take the Cayley graph of this thing, and then we use the quadratic part to define on this graph some kind of quadratic energy, which is given by this formula, which depends on the choice of the tangential vector. And then what we discover is that the graph that describes our operator, under Poisson bracket, is in fact to the subgraph of the Cayley graph, in which the edges have the property that the energy of the source and the energy of the target are the same. So somehow what you're saying is that since your operator commutes with this quadratic part, we are saying that that the quadratic part is preserved when there is an interaction. So here this defines you the graph. Now, how complicated is this graph? I hope I have some examples. So maybe now things are getting a little technical, but sorry, or maybe I'll skip this thing. I wanted to show you some examples. So at this point, in order to see that the graph is simple or complicated, there are further constraints on the set S. Because you want to avoid certain possible graphs. And there are certain graphs which you avoid because they give you some kind of resonances, which means that the vectors are in some special position, like the special position that I had here, except there are more complicated special positions, which are algebraic, geometrically defined resonances. So for instance, you want to do this. You take elements such that these points are finely dependent, and then you want to see that these things cannot be in a connected component of the graph. Okay? Because there is some resonance. And let me show you what the type of computations we do. So we take, for instance, we want to see that this kind of graph does not appear in our Hamiltonian. And now we write the condition that the energy is preserved on this graph. When you write the condition that the energy is preserved, we get the system of equations. This is the energy, and we should have that all these energies are equal to this energy here. Well, then we eliminate something, and we still have this unknown. This can be eliminated, and at the end we have a resonance. So we discover all these various kinds of resonances. If we can avoid, as we can, all these resonances, then we avoid all kinds of bad behavior in the graph. Once we avoid bad behavior in the graph, we have this geometric image of the graph, and which I've already given you this transparencies. And then we have the following theorem. Essentially, that the connected, simplify things, are connected components of the graph are finally independent. So suppose I can prove this. Now suppose you are in dimension 2. If you have that all components of the graph are finally independent, in dimension 2 there are at most 3 points which are finally independent, which means that my blocks will be at most 3 by 3. So I have decoupled my infinite dimensional system into systems which are either 1 by 1 or 2 by 2 or 3 by 3, which is a drastic reduction, because before it was infinite dimensional and now it's infinitely many independent systems of small dimension. Then there are some other technicalities which are essential actually for the algorithm, but maybe I should avoid them. Okay, so I think I still have maybe 5 minutes, and I'll use this 5 minutes just to give you some intuitive idea of what type of problems we get. So, first of all, about the proof. So, the proof goes in 2 steps. So, first, we have to find that these resonances to be avoided, and there are 2 types of resonances. One which is given by this dependence, and another type of resonance which has to be dealt with by the theory of determinantal varieties when things are finally independent. So, and then once you have all this game, then you prove that you can eliminate phases, and then you have to study all these infinitely many dynamical systems, which are fairly complicated still. So let me give you some ideas of kind of matrix blocks you get. So I just show you the blocks without, so for instance, you have a graph like this will give you a matrix like this, which will describe one block of the dynamical system. Or you actually will describe, one block, then there are other blocks which will be obtained by translation on this diagram. You have something like this, you'll get some matrix block like this. And then at this point you want to have some control on the eigenvalues as functions of psi. Because in order to perform the KM algorithm, you need that these eigenvalues are not they must be somewhat separated, these eigenvalues. Otherwise, when you perform the algorithm in the denominators, you get a lot of singularities which will destroy the algorithm. So you have to find out that these infinitely many matrices have separated eigenvalues. And this, of course, is a very complicated question. And I show you some of these things. So in order to understand this, you have to compute the characteristic polynomials. So you start take another matrix and compute the characteristic polynomials. And then you have to prove that all these characteristic polynomials have distinct eigenvalues. Infinitely many polynomials which have distinct eigenvalues. For generic values of the parameter psi, it means... now, of course, you have techniques in some sense. You write down resultants, discriminants, but they're impossible to compute. So you have to find out some other ways of doing it. And we found some strange way of doing it by arithmetic. And eventually we were able to prepare everything for the KM algorithm. And then once you start the KM algorithm, then you have to sweat a lot because then there are other issues. But that would require a completely different talk. I'm even unable to give, so you have to ask my daughter to give the other talk. Because the analytic issues are quite complex, even once you have resolved the algebraic issues. So that's another example. And you can imagine here I'm looking only at things which appear in dimension 3, but if you're in dimension 65, you will get enormous graphs, and so you have to have some way of handling all these monsters. Okay. So at the end, you get the characteristic polynomials of the combinatorial matrices are all irreducible over the integers and distinct. And this is the magic arithmetic structures which allows you to have the separation of eigenvalues, so the non-degeneracy Melnikov condition. And then you have eigenvalue separation, you have the solution of Hamiltonian, you have symplectic coordinates which diagonalize the Hamiltonian, and at that point you are ready to do the analysis. And at this point I stop. Okay.